So this is example 7. This might be a good one for you to try on your own. Pause the video, see how it works for you. It's worth to discuss how we know to do partial fraction decomposition, because I'm not going to title it or anything on the Unit 3 test. You're just going to have to jump in. I would say your best course of action is to try to let u equal the entire denominator. And when I do that, I would get 4x plus 7, and there's really no way to combat an x minus 13 with this. You're not really going to get out of the woods. Even with crafty like rewriting, this is a problem. And so if your du substitution doesn't work out and you can't kind of factor out a coefficient and make it work, then I want you to take a beeline for that denominator and say, all right, well, maybe I could do something else. Maybe I'll try that partial fraction decomposition. In order to try it, it has to factor. So see if you can factor that denominator. This is a quadratic. It opens up with 2x and x if you're going to try to factor it. I need factors of 3 to get the 7 in the middle, which sounds awkward, but it will work. They both have to be the same sign. They both have to be negative. You are at a successful moment to like actually consider a partial fraction decomposition. That denominator does factor. They are distinct linear factors again, so very similar setup to the last few that we have discussed. And we can kind of jump in and see what we can do. Now, the last two that we did only had like a coefficient in the numerator. This has an x minus 13. That does not change anything about what I'm going to do now. What I'm going to do is actually say, just like we did before, I'm going to take a look at this, colossal rational expression, and I'm going to reimagine. I'm going to see if there's an algebraic way to rewrite that, because I would really like to tone that down a little bit. So I'm going to write it. And I'm going to do the breakdown. Again, these are distinct linear factors. So that means I'm going to put a over 2x minus 1. I'm going to put b over x minus 3. And I'm going to go with the same process. There's nothing different about my path at this point. I am going to look at that rational equation, and I'm going to solve it the same way you've solved every rational equation in your life. Everybody gets multiplied by the LCD. When I do that, okay, on the first go here, both of those factors cancel out. All I have left is the x minus 13. That's all that remains. That's the point. On the right-hand side, on this first fraction, the 2x minus 1 cancels. You have the a multiplying the thing you couldn't get rid of, that x minus 3. Over here, you're going to have the b left over and the thing you couldn't cancel, which is the 2x minus 1. So you've just reimagined the statement in pink to the statement in orange, algebraically completely legal. Here's where you are going to be super crafty and say, oh, let me pay attention to what these factors are. I am going to decide, what if x equals 3? I'm choosing that intentionally because I really want these things to collapse down to 0. And I'm going to keep talking it out like, well, that means if x is going to be 3, anywhere there's an x in this statement in orange, I replace a 3. So that means I'm going to have 3 minus 13, a times 3 minus 3, and b times, 2 times 3 minus 1. So the whole point of saying x is 3, I know I have a negative 10 over here on the left-hand side, but the whole point of choosing 3 is so I have a times 0, and a times 0 is 0. Now what I have here is I have 6 minus 1 in the parentheses, that's 5, so I have 5b. And I think you can just kind of eyeball that, divide by 5, you have successfully figured out that b is negative 2. I am going to come at this again and say, well, let me do another crafty dream up. Or what if x is something else? And what would set that factor equal to 0 would be 1/2. What if x were 1/2? I'm going to do it. I'm going to go back to this statement here in orange, right? And I'm going to, anywhere I see an x, I'm going to replace it with a 1/2. So 1/2 minus 13. A is going to be 1/2 minus 3. And there we have it in for b. So anywhere there's an x, I replace a 1/2. Let's see what I have here. A half minus 13 is really negative, I'm going to switch to decimal, negative 12.5. 1/2 minus 3, that would be negative 2.5. And here is where you have your 1 minus 1, which is 0, and 0 times b is a big fat 0. So I can do this. I can divide both sides by negative 2.5. I know you don't have a calculator, but 2.5, well, will fit into 10 4 times, so there's an extra 1. So that means a is 5. And a is positive 5 because you have a negative divided by a negative. So here is the algebraic work here, right? There's no trig identities. There's no swaps going on. You're really relying on your really important algebra skills to get you through this process. And what that's going to allow for us is to say, oh, I can just keep working here, right? This was my original integral. All I did was factor it to get the second line. Let me just give myself some room here. What that means is now I can replace it with this. Well, it's a, which is 5 over 2x minus 1, right? Yep. Plus b, which is negative 2 over x minus 3. This is very manageable. I can handle those individual pieces there. I'm even going to consider them separately, and I am going to show the work on this because they are separate u substitutions, and I want to be careful here. You have a little bit of a different follow-through here on the first one, right? Because I'd have 5 over u times du over 2. So let me just finish that one out. That would be 5 halves the integral of 1 over u du, which of course is natural log, right? And then I'm just going to put the u in, 2x minus 1. When I come over here, right, I'm going to let u equal x minus 3. This one is more of a layup because du is dx. So I'm ending up with a statement where I have like negative 2 over u du. Well, that's going to be negative 2 natural log absolute value of u. So let's slide that in here. The u here was x minus 3, and we are good. Okay, there's different coefficients. We tend not to use those properties unless they're really, really easy to do. You might see them use some log properties, but I think this looks fantastic. Okay. So let's move on to example 8. This one's going to have a little bit of something different, right? We've been dealing with distinct linear factors for a while. Now we have example 8, which looks unbelievably more complicated. And don't overlook the fact that, hey, you should always be trying a basic u substitution first. And since I don't have anything composite, I would try to just, let u equal that entire denominator. But you can kind of see it's a train wreck here. You have a different quadratic follow through here. I can't cancel these. These are completely different quadratic expressions. They're not going to cancel each other out in any way. So again, not that it was wrong or silly or I shouldn't have done that. I don't want anyone to think any of those. You're just going to say, nope, don't look over there. I tried a basic u substitution because I thought it might work, and it didn't. Okay, so your next line of defense is going to be, hey, I see that denominator. That looks pretty good. I think that can factor. So you're going to go ahead and do that. And you can kind of see here I have a linear, that x all by itself, that is a linear factor. And then you have a quadratic factor, but let me see, does that reduce? I want to see if it's reducible or irreducible, because that changes my setup. So let's take a look. Factors of 1, both positive, yep, that works. And let's be really clear here, what you actually have is a repeated linear factor. See how that x plus 1 happens twice? Well, that's really going to change how I think about setting up this structure. I need to say, yes, this is definitely a partial fraction decomposition style question. I'm going to look at my setup and say, let me reimagine that colossal fraction, that rational expression, and see if I can organize it in a way that is simpler, that it's broken down into a lot of smaller pieces, and smaller pieces are usually easier to integrate. So let's talk about that setup. You're going to take this fraction, and let's set it up. You have that distinct linear factor, a over x. Now, to handle the repeated linear, you're going to have b over x plus 1 to the first, and then c over x plus 1 second. You need another fraction to represent every single power of that repeated linear factor. So since it was a power of 2, I have two fractions. I have x minus 1 to the first and x minus 1 to the second. They all just get a coefficient on top. That's really important because if you don't set it up right, you're not going to get the right breakdown. I'm going to come at this the same way I did all the other guys. You're going to multiply everybody through by the LCD. Everybody gets hit with the LCD, and you see what kind of gets left over in doing that. And we sort of take it from there. Okay, so on that guy on the left here, everything cancels, everything's gone. I'm left with the 5x squared plus 20x plus 6. On the right-hand side, the x's are gone. I have a times x plus 1 squared. On the middle guy, I have one of the factors of x minus 1 go away, but you still have this x and one of the extra factors there. Our last fraction, I'm going to have the c. The x plus 1 quantity squared is gone, but you have an x there, so I have c and x. And now we're going to get really crafty and efficient for what we decide to let x equal. So I'm going to look at it and say, well, this would be great. If I could just let x equal 0, this whole thing would fall to 0. So I'm going to do that as my first go here. I'm going to let x equal 0. That means anywhere there's an x, it's a 0. Well, that would be 5 times 0 plus 20 times 0 plus 6. And then what? I would have a times 1, I'll just say a, and then here, you'd have b times 0 times 1. Well, that's 0. And you'd have c times 0. You got a lot out of that one statement. You can read across really quickly. Obviously, a is 6. That's great. I'm going to make another really crafty move. I'm going to say, what if x were -1? I'm choosing that to get rid of these other factors here, right? So that means I'm going to let x equal -1 everywhere. All right, so let's be clear. That means 5 times -1 squared, 20 times -1 plus 6. -1 plus 1 is 0, so a times 0 is 0. Over here, -1 plus 1, that's going to be 0, so that whole term goes to 0. And then here I'm going to have c times -1. I'll just put minus c. So what do I have? I have 5 minus 20 plus 6 equals -c. So -9 equals -c. That tells me c is 9. That's a nice number. This is great. And at this point of the game, you're sort of out of good choices, right? Like you don't have any other great imaginative thing to let x equal so that one of those factors collapses because you had a repeated linear factor. It's okay. You can choose anything you want. There is actually nothing special about the 0 and the -1. They're just mega efficient. You can let x equal 12 if that's your favorite number. I don't want to go that big. I'm kind of lazy. I usually choose like 1 or 2. I'm just going to make up. It doesn't matter what you make up. The x could be 3. It could be 5. It could be a half if you really love fractions, whatever you want to do. I'm going to choose 1 because I think it's easy. So I'm going to plug 1 in. I'm just going to dream up. You need another one because you still have this missing coefficient. You don't know what b is. So make up any x value you want. Totally your call on what that extra guy is. But anywhere there's an x, you're replacing it with a 1. So what does that mean? I'd have 1 plus 1 squared. Well, that's 4a. Over here, let's see, if x is 1, I'd have b times 1, that's b, and then 1 plus 1, that's 2. So that would be 2b. The last piece of the puzzle here is that, remember, x is 1, so that's a c. All right, so what do I have? I have 5 plus 20 plus 6. That is 31. What do I have here? I have 4 times a. Well, remember, a is 6. Oops. So 4 times a is 24. I don't know b. That's the whole point, so I have to leave that alone. 2b. That's all I have. And then I already figured out that c was 9. So I have 31 on the left let's see, 24 plus 9, that's 33. So move the 33 over. Negative 2 equals 2b, so that tells me that b is negative 1. So this is great. I now have a path to getting this integral ironed out for myself. Instead of handling this colossal monstrosity highlighted in green, I can look at smaller itty-bitty pieces. So I'm going to come down here just to give myself some more room. So what does this mean? Well, it means a is 6, so I can break this up into 6 over x. Separately from that, I can consider b over x plus 1. And separately from that, I can consider c over x plus 1 squared. This is much better to handle. Think about just individually, we're going to work this out, right? Like this is totally, totally doable. Right away, I can get my answer on the first one. I'm just going to pull the 6 out. That's going to be 6 natural log absolute value of x. It's just a basic rule. I'll say the same thing on the other guy here. You just pull out the negative 1, right? This technically is a little u substitution. We can go full throttle and write everything down here. I don't want to lose anybody. You are letting u equal that denominator. So what do I have? 1 over u du. Well, that's natural log absolute value of u. Okay. So what does that bring me to? That brings me to the negative natural log absolute value of x plus 1. So let me not forget about this first part of my answer over there. I'm just going to rewrite it. And now let's get into it on the last one. What do I have there? Well, let's see. I have 9 times the integral of 1 over x plus 1 quantities squared. Now this is also going to be a u substitution where u equals x plus 1. Now let's just be careful what's happening here. I have 1 over u squared, and this was my line of defense to kind of help you here. This is u to the negative 2. This is a power rule. This is not a natural log antiderivative. This is add 1 to the exponent and divide by your new exponent. That's what's going on here. So let's be really, really careful about that. So what is that? That's negative 9 over u. So let's go full throttle and put all of these puzzle pieces together here. That would be negative 9 over x plus 1. And I'm just going to rewrite the other parts of my answer to make sure I have one smooth, cohesive line for my antiderivative. Okay, so it's super helpful to break these up into smaller little components because they're much more manageable to get an antiderivative to.